Welcome to Pastor Victor's Academy. Embark on a journey through the world of engineering mathematics and electrical engineering with our educational tutorials designed specifically for engineering students. Whether you're mastering calculus, solving complex circuit problems, or exploring power systems, Pastor Victor's Academy is your ultimate learning companion. Join us as we break down complex concepts into clear, easy-to-understand lessons, helping you build the foundational knowledge and skills needed to excel in engineering mathematics and electrical engineering courses. Subscribe now to kickstart your learning journey and gain the confidence to tackle engineering challenges head-on. Let's unlock the world of mathematics and electrical engineering together, one lesson at a time.
Welcome to Pastor Victor's Academy. I'm glad you're watching. Thank you so much. I've done several videos and one of them is the limit of a function, which I think would help you understand some of the things I'll be talking about in this video. And also the previous video I did was about finding the gradient of a curve at a point. I also gave a brief introduction to differentiation, and I remember saying that differentiation is about getting the derivative of a function, and the derivative of a function is the function of the slope of that particular function. In other words, when we're able to get the derivative of a function, we can get the slope of that function at any point on the curve. So in this lesson, I want to talk about the derivative of different kinds of functions. So please, I want you to pay attention as we go on in this lesson. I can assure you that you will learn a lot in this very lesson. So the derivative of a function mathematically is given as dy over dx. And that's the same thing as the limit of change in y over change in x as change in x tends to 0. So here we have change in y over change in x. And here we have dy dx, which means that change in y by change in x tends to dy dx. That's what it means, as change in x tends to 0. So that's what the derivative of the function is. And for us to be able to get the derivative of different kinds of function, that's for the basics, for the fundamentals. We want to get the limit of some of the functions we'll be needing as x tends to 0. So here we have solved the following, and the first one we have is limit of sin x over x as x tends to 0. The second one is limit of minus 1 plus cos x over x as x tends to 0. And the third one is limit of e to the power kx minus 1 over x as x tends to 0. Then the fourth one we have is limit of ln 1 plus x over x as x tends to 0. So we'll be working with 5 decimal places for the answer we'll be getting. So why are we interested in finding these limits? Because we'll be needing them for the derivative of the functions we'll be looking at. So the first one we have is limit of sin x over x as x tends to 0. And this is equal to 1. We'll find out if that's true. So because we have a mixture of trigonometric function and x, that means we'll be getting the value of x in radians and in degrees. So for the degrees, you use this. If x is given in radians, we'll have x over 2 pi times 360. That gives you the equivalent in degrees. Then if x is given in degrees, to convert to radians, you just say t over 360 times 2 pi equal to x. So it's just the same thing. It's making x the subject of the formula in this function. Now remember that the limit of a function is said to exist if the right-hand side limit is equal to the left-hand side limit. In other words, when you're approaching a particular value of x from the right and from the left, it should give you the same answer. So here we are talking about 0, and we need to approach 0 from the right and also from the left. Here we have x, and we have minus 0.01, minus 0.001, then minus 0.000001. Then approaching from the right, we have 0.01, 0.001, 0.0000001. So remember that this is greater than this, 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 this is greater than this. So what happens to the function for each value of x? So for minus 0.01, this is the equivalent in degrees. This is the equivalent in degrees. degrees. For this one, this is the equivalent in degrees. So you can try using the formula and you see that you get approximately the same answer for the degrees. So what do? We have seen x over x, and this x will be in degrees, whereas this x will be in radians. So you use this guy here and use this guy here. You'll be getting 0.99999. Then do the same for this guy. You have 1.00000. Do the same for this guy. You have 1.00000. That's, I'm working with 5 decimal places for my answer. Then do the same for the right hand side. You get this, you get this, and you get this. So you notice that as we are approaching 0 from the right, we're actually approaching 1. That's the function is approaching 1. So here we had 0.99999. Then here we had 1. Then for the next one, we still had 1. The same thing happened for the left-hand side. We initially had 0.99999. Then for the next value of x, we had 1. Then for the next one, we still have 1. So which shows that the limit of this function as x tends to 0, that means as we go close to 0 from the right-hand side and from the left-hand side is equal to 1. So we'll be calculating for minus 1 plus cos x over x. Here we have the limit of minus 1 plus cos x over x as x tends to 0. So it's still a mixture of trigonometric function and x. So in other words, we have to get the equivalent of x in degrees. And we are using the same set of values we used in the previous calculation. So how do we know it's 0? That means we'll be approaching 0 and see what happens. So for the first guy, we had 0.00500. So what are you supposed to do? You're saying minus 1 plus cos this value over this value. This is the degrees, this is the radians. So minus 1 plus cos this value over this value. And you'll be getting 0.00500. Remember that this is not 0. So we'll keep going close to 0 and see what happens. You take the next guy, we'll have 0.00050. So this is closer to 0 than this. Then what do? Go to the next guy. You're having, that's for 5 decimal places, you're having 0.00000. And that's the same thing as what? 0. And for the next one, that's for the right hand side, we'll have this 0.00000, which is also the same thing as what? 0. Then we're having minus 0.00050. Then we're having minus 0.00500. So you can see that we're having negative values, we're having positive values, but on going very close to 0, we arrived at 0 for both sides. So in that case, the limit of minus 1 plus cos x over x is equal to 0 as x tends to 0. Now let's solve for the next one. We have limit of e to the power kx minus 1 over x as x tends to 0. So I used k here because you could substitute k with any value. So k can be 1, k can be 2, k can be 3, k can be a decimal value. Any value you want for k, just put it and you work with it. So for my own calculation, I'll be using 7 as the value of k. We have limit of e to the power 7x minus 1 over x as x tends to 0. Now, when we begin to check, we'll discover that our answer is 7. So here we don't have a trigonometric function, we don't have sin x, we don't have cos x, we don't have tan x. So in that case, our x will be in radians. That will be a normal number. So x, we're having minus 0.01, minus 0.001, minus 0. We'll have 6 zeros here, then we'll have 1. Then for the right hand side, we'll have this, but we don't have a negative sign. Then we'll have this, we'll have this. So let's see what happens. We have e to the power 7x minus 1 over x. Now use this number for the power and use it for the denominator. That's, here you have x, you put this number. For the first one, you'll be having 6.76062. This number is close to 7, but it's not 7. Because if you approximate, you'll be having 7, but it's not 7. So what do? We'll go closer to 0. We'll be having 6.975556. We are still very close to 7, but it's not 7. We'll keep going close. So the closer we get to 0, we realize that our function is approaching 7. For this value, we are having 7.00000. That's for 5 decimal places. Then, let's see what happens for the right-hand side. We also got 7. That's for 5 decimal places. You have to approximate. You're working with 5 decimal places, you're working with 5 decimal places here. So when you approximate, you'll be getting 7 for both of them. Then, whereas for here, we're having 7.02456, and for here, we're having 7.25082. So this number is bigger than this is bigger than this. So it means that as we're approaching 0 from the right, we're approaching 7. And as you're approaching 0 from the left, you're also approaching 7. So our answer is 7. So what happens, assuming we have 3 here, what would have been the answer? The answer would be 3. Assuming we have 4 here, what would have been the answer? The answer would be 4. So the limit of e to the power kx minus 1 over x as x approaches 0 is k. So whatever you choose as your k, that's the limit. So that's it for this one. Let's look at the fourth one. Limit of ln 1 plus x over x as x tends to 0. Here we have limit of ln 1 plus x over x as x tends to 0. What is it? 1. How do we know? Just do your calculations and you will know. Here we have x minus 0.01 minus 0.001 and so on. Now, because this is not a trigonometric function, we will not be using the equivalent in degrees. We'll just work with the value we have. So these are the values we have. Now, we have the function as ln 1 plus x over x. Use this value here and here. For the first guy, you're having 1.00503. And that seems like 1, but I want to be sure we keep going close to 0. For the second guy, we're having 1.00050. So this is closer to 1 than this. Then for the next guy, we are having 1. That's working with 5 decimal places. Then coming from the right, the first value we have, that's 0.01. We're having 0.99503. Assuming we want to do approximation, we would have gotten 1. But we want to be sure, then we take the next value closer to 0. We got 0.99950. This is very close to 1. Then we take another value very close to 0 and we realize that we got what? 1. So you can see that the right side limit is 1. The left side limit is 1. So in that case, the limit of the 1 plus x over x is equal to 1. So please write down your answers on your notebook because we'll be needing these limits to get the derivatives of the functions we want to look at. So that takes us to the next thing, the derivative of different kinds of function. Now the first function we want to look at is the constant function. Now keep this in mind that the y dx is equal to the limit of change in y over change in x as change in x tends to 0. So we want to get the derivative of the constant function. And the constant function is giving us y equal to c, y equal to k, whatever you want to call it. Now, what is your c? Your c is just a number. So there is no x in the function. You just have a number. So c could be 1, c could be 2, c could be 3, or a decimal number. Now, we have the graph. Here is y, here is x. So we have x1, x2, x3, x4, x5. So assuming we are using the interval of 1, we'll be having 1, 2, 3, 4, 5. So what did you notice is that when x is 1, we still had c. When x is 2, we had c. When x is 3, we had c. When x is 4, we had c. When x is 5, we also what? Had c. So the function does not change with x. That's why it's called a constant function. My c here can be 1, can be 2, can be 3, or any number. But once you pick the number, it doesn't change with changes in x. It's just constant. So how do we find the derivative of a constant function? We say that at x1, comma, y1 is equal to c. Then at x2, comma, y2 is also equal to what? C. It does not change. Now let's take the difference of the two functions. That's change in y is equal to y2 minus y1, which is the same thing as c minus c, and that gives us what? 0. But remember that we are looking for change in y over change in x. So what do? Divide this by change in x. So if you're having that change in y over change in x is equal to 0 over change in x, which is also what? 0. Now we are looking for the limit of this slope, that's change in y over change in x, as change in x tends to 0. So if you check my video on the limit of a function, you will notice that I said that the limit of a constant function as x changes or tends to a particular value is still that value, that's the constant. So in this case, our constant is 0 because this is a function. Changing over changing x gave us 0. which is also a constant function. By the time we take the limit as the limit of change in y over change in x, as change in x tends to 0, there's no change in x here. This is a constant function. In that case, our answer is still 0. So what does it mean? That the derivative of a constant is 0. The derivative of a constant is 0. Whether the constant is 1, 2, 3, 4, 5, it doesn't matter. So dy dx, when you differentiate a constant function, you'll be having 0. Let's look at the next function. So the next function we'll have is the linear function. It's called a linear function because when you plot the graph, you'll be having a straight line. So we'll have y equal to ax plus c. This is the equation of the linear function. So what will be the derivative? That's the y dx of the function. You see at x1, comma, y1 is equal to ax1 plus c. Now at x2, y2 is equal to ax2 plus c. Now, please take note, y2 minus y1 is changing y, and x2 minus x1 is changing x. So, making x2 the subject, we're having that x2 is equal to x1 plus changing what? X. So, we'll be working with this. Now, let's get our change in y. We'll be having a into x1 plus change in what? X plus c. And change in y is equal to y2 minus y1. And that gives us a into x1 plus change in x plus c minus ax1 plus what? Plus c. So we're having c here, we're having c here. Both will cancel out. We're having ax1. Let's open this bracket and see what we have. So change in y is equal to ax1 plus a change in x plus c minus ax1 minus c. C minus c gives us 0. So these two are out. ax1 minus ax1 gives us 0. So these two are out. Change in y is equal to a change in x. So we're looking for change in y over change in x. So divide by change in x. You're having a. Now let's take the limit. You can see that change in y over change in x is a. And a is a constant. It doesn't change with what? With x. So in that case, the limit of change in y over change in x as change in x tends to 0 is equal to what? A. So that's the same thing we did for the previous function. Assuming a is 0, we'll be having 0. But in this case, a will not be 0. So a will either be 1, 2, 3, depending on what you have as your a. So that's what the derivative of a linear function, the coefficient of x. Remember that if you have the equation of a linear function, the coefficient of x is the slope, then this constant is the intercept. So you can say that it's just the same thing. Let's talk about the next function. The next function is monomial functions. A monomial function is expressed like this: y equal to ax to the power n. So your n is the index, then your a is the coefficient of x. So we'll be handling 3 types. We have ax squared, and ax to the power 3. For the first one, y is equal to ax. So when we have x1, that means y1 is equal to ax1. And when we have x2, comma, y2 is equal to ax1 plus change in x. Remember that this is the same thing as x2. So taking the difference of y, we're having that change in y is equal to ax1 plus a change in x minus ax1. So what do we have? ax1 is subtract ax1. Change in y is equal to a change in x. Then divide by change in x. You'll be having a. Now take the limit as change in x tends to 0. Since this is not varying with change in x, the limit will be change in over change in x as change in x tends to 0 will be a, because this is a constant function. That's change in over change in x is a constant function, which is a. So the limit will still be what? A. So that's that for y equal to ax. And let's look at y equal to ax squared and see what happens. Now, for x1, we'll be having y1 is equal to ax1 squared. Then for x2, we'll be having y2 is equal to a into x1 plus change in x squared. Because this is our x2, x1 plus change in x. Y2 is equal to a into x1 plus change in x. X1 plus change in x. So what do we have? We'll be having a x1 times x1, that will be x1 squared. X1 times change in x, that will be x1 change in x. X1 times change in x, that will be x1 change in x. Change in x times change in x, that will be change in x, all what? Squared. So what do we do? This gives us a x1 squared plus a2 x1 change in x. Why do we have 2 here? This plus this. And for the next one, we're having a change in x squared. So what will be our change in y? Our change in y will be this minus this. So we'll be having change in y equal to a2 x1 change in x plus a change in x1 squared. That's after we've removed ax1 squared, which is this. So dividing by change in x, we'll be having a2 x1 plus a change in x. Now, what do? We take the limit of this function as change in x tends to 0. So what will be the limit? Well, the limit of change in over change in x as change in x tends to 0. So in the equation, we only have change in x here. As change in x tends to 0, a change in x will be tending to 0. That means a change in x becomes 0. We only left with a2x1. So this gives us a2x1, which is the same thing as 2ax1. So the derivative of y equal to as squared is the same thing as the y dx is equal to 2ax. So let's take the third example before we move to the next thing. Y is equal to ax to the power 3. What do we do? At x1, y1 is equal to ax1 to the power 3. At x, y2 is equal to a, then we have x1 plus change in x. Then we have to the power of 3. So this is the same thing as ax1 cube, a3x1 squared change in x, plus a3x1 then change in x squared, plus a change in x to the power 3. So subtracting y1 from y2, we're having change in y is equal to, we have ax1 cube. So we remove ax1 cube from it. We're having a3x1 squared change in what? X plus a3x1 change in x squared plus a bracket change in x what? Cube. So what do? We are looking for change in y over change in x. So we're having a3x1 squared then plus a3x1 change x plus a change in x squared. Remember we had cube here, but now we're having square here. We had square here, but we're having change in x here. We had change in x here, but we're having nothing here because we divided through by change in x. So let's take the limit as change in x approaches 0, which means as change in x tends to 0, what happens to change in y over change in x? So in that case, we'll be having limit of change in y over change in x as change in x tends to 0, which is equal to dy dx. And this gives us, when we put 0 here in the place of change in x, this becomes 0. Put 0 here in the place of change in x, this becomes 0. This does not vary with change in x. So in that case, we're having a3x1 squared. So if we remove this script 1, it's just the same as saying 3ax what? X squared. Now let's compare our results to see what is common among the 3 derivatives we got. So for the first one, we had a. For the second one, we had 2ax. And for the third one, we had 3ax squared. So you can see when we had x here, then the derivative is a. When we had 2 here, the derivative is 2ax. When we had 3 here, the derivative is 3ax squared. That gives us the pattern n a x to the power n minus 1. So for every monomial function, the derivative is n a x to the power n minus 1. So in this case, n was 1, 1 minus 1, 0. A number to the power 0, that's your laws of indices, will give you 1. Then here we are having that 1 multiplying. So we're having 1 into a into x to the power 1 minus 1, which is the same thing as 1 into a into x to the power what? 0. This is 1, this is 1. A times 1 still gives you what? A. So that's how we got this. Then for the second one, we had 2, and that's our n. What do? We say 2 into a, then we have x. We said n minus 1. So what's our n here? Our n is 2, so 2 minus 1. That gives us 1. So we're having 2ax to the power 1, and that's the same thing as 2a x. So here we have it. Then for the third one, our n is 3. So we write 3, write a, then we write x to the power 3 minus what? 1. 3 minus 1 is 2. That gives us 3a x to the power 2. That's what we have here. So the y, the x for every monomial function is n a x to the power n minus 1. Your a is the coefficient of x. Then your n is the degree of the monomial function, that's the power of x. Then you're having the derivative to be dy dx equal to n a x to the power n minus 1. Assuming the coefficient is 1, so a here becomes 1. Then assuming the power is 1, then you'll be having 1 into 1, x to the power 1 minus 1, and everything becomes what? 1. That takes us to the next function. The next function we'll have is the exponential function. So we'll have e to the power x and a to the power x. So e here is a particular number in mathematics, whereas a could be any number. So we'll first off deal with this before dealing with this. So what do we have? Y is equal to e to the power x, meaning that y1 is equal to e to the power x 1. And that is the same thing as e to the power x plus change in x. What do? We say y1 minus y. That's the same thing as change in y. So change in y is equal to e to the power x plus change in x minus e to the power x. Remember that this is the same thing as e to the power x times e to the power change in x. Then we are saying minus e to the power what? X. So we have a common factor, and that means that change in y is equal to e to the power x. In brackets, we're having e to the power change in x minus 1. So dividing by change in x, change in y over change in x is equal to e to the power x, e to the power change in x minus 1 over change in x. So taking the limit of this, limit of change in over change in x, as change in x tends to 0. Now, remember that when we did limits, we said that the limit of the product of two functions as x tends to a particular value is the product of the individual limits as x tends to that particular value. So here we are looking at limits of change in over change in x as change in x tends to 0. This is not x, this is change in x. So in that case, we have product of two functions. This is a function, e to the power x is also a function. But here e to the power x is treated as a constant function. Why? It does not vary with change in x. But this function varies with what? Change in x. Because we have change in x and we have change in x here. So if we take the limit of a constant function as change in x tends to 0, we still get the constant, which is e to the power x. So in this case, we're having e to the power x into something. That's the limit of this guy. If you go back when we did limits of e to the power kx minus 1 over x as x tends to 0, we said that this is equal to what? K. Now, let's rewrite this. So we say limit of e to the power k change in x minus 1 over change in x as change in x tends to what? 0 is also equal to k. So whether you write x or you write change in x, just know what you're working with. This gives us k. So let's compare. What do we have? K change in x minus 1 over change in x. And that's the same thing we have here. E to the power change in x minus 1 over change in x, implying that our k here is 1. So That means when we take the limit of this function as change in x tends to 0, we'll be getting what? 1. So we'll be having e to the power x into 1, and that gives us e to the power what? X. So if y is equal to e to the power x, the y dx is equal to e to the power what? X. Now the question will now be, what if we have e to the power kx? We'll just do the same thing. We'll be having y1 equal to e to the power k, open bracket, x plus change in what? X. So your change in y will now be e to the power kx, then plus k change in x minus e to the power what? Kx. So you can see that we have a common factor when we expand this. We'll be having e to the power kx into e to the power k change in x minus e to the power kx. So you pick your kx, e to the power kx. So change in y is equal to e to the power kx into what? E to the power k change in x minus 1. So what do we have? Divide. We'll be having change in y over change in what? X. And that gives us e to the power kx into e to the power k change in x minus 1 over change in what? X. So if we take the limit of change in over change in x as change in x approaches 0, there is no change in x for this guy, so it is a constant. We treat it as a constant. But we have change in x and we have change in x. And when we take the limit as change in x tends to 0, we'll be getting k. So it means that the limit of change in y over change in x is equal to e to the power kx times k. That's k for this guy and this for this guy. So what does it mean? Dy dx is equal to ke to the power what? Kx. Now take for instance k is 1. Just as we had initially. What do we have? We have 1 into e to the power 1 x, and that's e to the power what? X. So you can see that from here, we can even get the derivative for e to the power x. So let's watch the next one. Remember from logarithm, ln a to the power x is the same thing as x ln a. Then making a to the power x the subject of the formula, we'll be having a to the power x equal to e to the power x ln a. Now, we have y equal to a to the power x, so we'll have to bring this here. Then that gives us e to the power x ln a. So our y1 becomes e to the power x plus change in x into ln a. By the time we expand this, we'll be having e to the power x ln a into e to the power change in x ln a. So our change in y will become e to the power x ln a into e to the power change in x ln a minus e to the power x ln a. So we have a common factor. We'll be having e to the power x ln a into e to the power change in x ln a minus 1. So we'll be dividing both sides of the equation by changing x. In that case, we'll be having over change in x, then over change in x. So we'll take the limit of change in y over change in x as change in x tends to 0, and that's the same thing as dy dx. So e to the power x ln a is the same thing as a to the power x. So we'll have a to the power x. Why is the limit a to the power x? Because there is no change in x here. So we'll have to treat this guy as a constant. So the limit of a constant is that constant. So in that case, the limit of e to the power x ln a as change in x tends to 0 still gives us what? E to the power x ln a, and that is the same thing as a to the power x. Now what will be the limit of this guy? Remember that the limit of e to the power kx minus 1 over x is equal to k. Now we'll compare. What does it mean? That the limit of this guy is equal to what? Ln a. That means dy dx is a to the power x what? Ln a. Now, let's assume that a is e, because we said a can be e, a can be pi, a can be any number. Now, if a is e, we'll be having that dy dx for y equal to e to the power x. That means a is e, so we're having e to the power x. It gives us what? E to the power x ln e. Ln e will give you 1 because this is something as log e base e. So in that case, we'll be having dy dx is equal to e to the power what? X. So you can see that we're able to get the derivative of e to the power x from the derivative of e to the power x. That takes us to the next thing. That's derivative of logarithmic functions. For logarithmic functions, we'll have ln x and log x base a. So this is written as log x base e. But as this is log x base a. A is any number. So we want to look at ln x first. That's y equal to ln x. It implies that y1 is equal to ln x plus change in x. Then change in y is equal to ln x plus change in x minus ln x. Now, if you still remember your rules, that's for logarithm, what do we have? Change in y becomes ln x plus change in x over x. And that's because we have a negative sign here. Remember in logarithm, when you have a negative sign, it becomes division. So change in y gives us ln 1 plus change in x over x. Now when we divide by change in x, we'll be having change in over change in x is equal to ln 1 plus change in x over x. So let's assume that change in x over x is equal to h. It means that change in x is equal to hx. Now, looking at this equation, it also means that if change in x tends to 0, that means h will also be tending towards 0. That's, if we have 0 here, definitely h will be 0. That's what it means. As change in x tends to 0, h tends to 0. Substituting for change in x over x in this equation, we'll be having change in y over change in x is equal to ln 1 plus h. Now, what's our change in x? hx, so over hx. So we'll be having that change in y over change in x is equal to 1 over x ln 1 plus h over h. So the next thing we'll do is to take the limit as change in x tends to 0. Now, as change in x tends to 0, change in y over change in x becomes dy dx. Now, because x is not changing x, we'll treat it as a constant. We'll be having 1 over x. That's for the limit. Now, as change in x tends to 0, what happens to h? H will also be tending to 0. And remember that the limit of ln 1 plus x over x as x tends to 0 is 1. So the same thing is applicable here. The limit of ln 1 plus h over h as h tends to 0 will be giving us what? 1. So dy dx is equal to 1 over x. So the derivative of ln x is 1 over x. Now let's look at the next one. We have that y is equal to log x base a, which is the same thing as ln x over ln a. You can use your calculator to confirm it. We have log 100 base 10, the same thing as ln 100 over ln 10. Whatever number you put here or here, try it, you get the same answer. So using this relationship, we'll be able to get the derivative for y equal to log x base a. So in that case, we'll be having that y1 is equal to 1 over ln a into ln x plus change in x. Now, our change in y becomes 1 over ln a into ln x plus change in x minus 1 over ln a into ln x. So have a common factor, 1 over ln a, 1 over ln a. So change in y is equal to 1 over ln a. We'll open our bracket, then we take this and this. That gives us ln x plus change in x over what? X. Now, what happens by the time we divide both sides by change in x? We'll be having that change in y over change in x is equal to 1 over ln a, then into ln x plus change in x over x then divided by what? Change in x. So what do we have? X will divide x. So we are having this to be 1 over ln A into ln 1 plus change in x over change in x. So doing the same thing we did in the previous example, we'll be having that change in y over change in x is equal to 1 over ln A into ln 1 plus h over hx. Now we bring out x, so we're having that change in y over change in x is equal to 1 over x ln A into ln 1 plus h over h. So we'll take the limit as change in x tends to 0. This is x ln A, that's 1 over x ln A. It is not dependent on change in x. So in that case, we'll be having that dy dx is equal to 1 over x ln A. Now, the limit of this guy as change in x tends to 0 will be 1. So that gives us 1 over x ln A. So I'll have a log of x base A. The derivative will be 1 over x ln A. Now, let's assume that A is E. So we're having that dy dx is equal to 1 over x ln E. And ln E is 1. And that gives us 1 over what? X. So you can see that if A is E, we'll be having ln what? X. And the derivative of ln x is 1 over x. So from here we got the same answer. Let's look at the next thing. So the next function we are considering is trigonometric functions. We want to get the derivative of trigonometric functions. And we'll focus on sin x and cos x. So if we can get the derivative of the two of them, it's easy to get the derivative of tan x and other ones. So what do? We'll have y equal to sin x. Then y1 will be equal to sin x plus change in x. Then change in y will be sin x plus change in x minus sin x. Now from trigonometric relationship, sin A plus B, that sine of A plus B is the same thing as sin A cos B plus cos A sin B. So what do? We apply it here by expanding sin x plus change in x. So this gives us sin x cos change in x plus cos x sin change in x minus sin x. So looking at the equation, what do? We collect like terms. Change in y becomes, we'll have sin x here and we'll have sin x here. So in that case, we'll be having sin x into cos change in x minus 1. Then we are having plus cos x sin change in x. Then we divide by change in x. So we'll have change in x and we'll have change in x. So looking at this, the next step to take is to take the limit of change in y over change in x as change in x tends to 0. And that gives us dy dx. So what will be the limit of sin x as change in x tends to 0? Of course, it will be sin x. So we'll be having sin x into. So what will be the limit for this one? Already we did cos x minus 1 over x, and that's 0. So we're having 0 here. Then plus, for this guy, we'll be having cos x. Then for sin change in x over change in x, the same thing as saying sin x over x as x tends to 0. That gives us what? 1. So dy dx is equal to what? Cos x. So the derivative of sin x gives us cos x. Let's look at the derivative of cos x. Now, y is equal to cos x, implying that y1 is equal to cos x plus change in x. Let's expand this. Cos A plus B is the same as cos A cos B minus sin A sin B. Now we apply this here, we'll be having cos x cos change in x minus sin x sine change in x. So change in y is equal to cos x cos change in x minus sine x sine change in x. Then we'll have minus cos what? X. So the next thing we do is to factorize. We have cos x here and we have cos x here. So in that case, our change in y is equal to cos x, open your brackets, cos change in x, then we'll be having minus 1 here, then minus sin x sine change in x. Now divide by change in x. Here we'll be having over change in x, and here over change in x. So the next thing to do is to take the limit of change in y over change in x, as change in x tends to 0. So that gives us our dy dx, which is equal to, so for this guy cos x, we'll be having cos x. Then for this guy, we'll be having 0. Then for sine x, we'll be having sine x. Whereas for sine change in x over change in x, we'll be having what? 1. Cos x times 0 is 0, so dy dx is equal to 0 minus sine x, which is equal to minus sin what? X. So that gives us the derivative of cos x. Now the next thing I want to look at is differentiation techniques. There are rules and methods used to find the derivative of compound or complex functions. So we've been looking at simple functions, but the truth is that we'll not just be dealing with simple functions. We'll meet complex functions, we'll meet compound functions. For example, a polynomial function is a compound function. So the question is, how do we handle a polynomial function when we meet it? So that's the essence of knowing these techniques. So the first one we have is that dx dy is equal to 1 over dy dx. So what this means is that dy dx is the inverse of dx dy. Now let's say that y is equal to 3x squared. Now our dy dx, when we did differentiation of monomial functions, we will multiply 2 with 3 and we'll be having 6x. So let's take note of this answer 6x. We want to see if dx dy will be 1 over what? 6x, because we said the x dy is 1 over dy dx. So let's make x the subject of the formula in that equation. So x squared is equal to y over 3, which implies that x is equal to root y over 3. That is the same thing as y to the power half over 3 to the power half. So what do we do next? The x dy is equal to half minus 1. That will give you minus half. But before you subtract, you would have used half to multiply this. That's for differentiation of monomial functions. So in that case, we will be having half y to the power minus half over 3 to the power half. Now let's come to this side. We'll be having half over, since this is negative sign, from laws of indices, we know that it will come down. Then we'll be having y to the power half times 3 to the power half. This is the same thing as half over root 3 times y. That is half over root 3y. Now, what's our y? We'll go back to the original equation. Y is 3x squared. So we'll substitute for y in the equation. We'll be having that the x dy is equal to half over root 3 times 3x squared. This gives us half over 3 times 3, 9. So root 9x squared. Root 9 is 3. So we're having half over 3, and root x squared is x. So the x dy will is equal to 1 over 2 times 1 over 3x, and that gives us 1 over 6x. So you can see that we also got 1 over 6x. So which proves that the x dy is equal to 1 over the y dx. So which also implies that the y dx is equal to 1 over the x dy. So if you take the inverse of this, you will get 6x, and that's our dy dx. You can do the same with trigonometric functions, any kind of function. It will just give you the same answer. Now, the next one we have is dy du dot du dx is equal to dy dx. This dot here is just multiplication, so don't think it's something else. We'll multiply dy du with du dx, just like you would have in normal algebraic equations. This will cancel this and we'll have dy dx. So let's see if that's true. Say for instance, you have that u is equal to 3x and y is equal to u squared. That is 9x squared. So what this means is that dy dx is equal to 18x. How? 2 times 9, 18x. So then 2 minus 1 for the power, that's 1. So we're having 18x for dy dx. Let's see if by applying this, we can also get the same answer. So we're having dy du. dy is y equal to u squared. So dy du will be 2u. Now the next thing we are looking for is du dx. Here u is equal to 3x. So du dx is equal to 3. We said multiply this with this. So you'll be having that dy du dot du dx is the same thing as 2u times 3, and that gives us 6u. We'll come back to our equation. We'll have that u is equal to 3x. So in that case, we'll be having 6 times 3x, which is equal to 18x, and that is our dy what? Dx. So you can see that we got 18x and we got 18x to confirm that dy du multiplied by du dx will give you dy dx. Okay, let's look at the next technique. The next techniques we want to look at are the sum rule and difference rule. So what's the sum rule about? We said if u and v are functions of x, so in this case, u is a function of x and v is also a function of x, and y is equal to u plus v, then dy dx is equal to du dx plus dv dx. Now for the difference rule, the same thing applies. We're having if y is equal to u minus v, then dy dx is equal to du dx minus dv dx. So let's use one equation as an example. So we are having something like y is equal to 2x plus 5. Remember that this is a linear function. And if you can still remember what we did, that dy dx for a linear function is the same thing as what? M. And in this case, our m is 2. So let's see if we get the same results. We're having y equal to 2x plus 5. Here, 2x is a monomial function. So differentiating this, we'll be having that dy dx is equal to 2 plus differentiate 5 is a constant function. So because it's a constant function, the derivative will be 0. So we are having 0, and that gives us what? 2. So you can see that dy dx is the same thing as du dx plus dv dx. So the question now would be, what if we have minus 5? We are having y equal to 3x minus 5. Then dy dx is equal to differentiate this, you have 3. Differentiate this, you have what? 0. 3 minus 0 is still 3. And that's our what? M in the linear function, whereas 5 is our C. That's what it is. Let's assume that y is equal to 3x squared plus sine x minus 20. And you are asked to get the derivative of y. simply differentiate each of the functions of x individually and you take the sum of the difference. So dy dx is equal to 2 times 3, 6x. And here we have sum, that's plus. Then sin x, when you differentiate sin x, you have what? Cos x. Then differentiate a constant, you have 0. So our answer becomes 6x plus what? Cos x. I want us to touch one more example before we go to the next techniques. Here we're having y equal to log x base 2 plus ln x minus cos x plus e to the power 3x. So all these things are functions of x and they are just basic functions. Cos x, e to the power 3x, ln x and log x base 2. Looking at this, you may say that it is complex because we have a mixture of functions, but it's not really complex. Here we have log x base 2 ln x cos x e to the power 3x. So when differentiating individually, we can get dy dx. So let's go. Dy dx is equal to, when you differentiate log x base a, you have 1 over x ln a. So in that case, you are having 1 over x ln 2. Then plus this one, when you differentiate ln x, you have 1 over x. Then minus, when you differentiate cos x, you have minus sine x. Then when you differentiate e to the power 3x, if you can still remember what we did, it will now become 3e to the power 3x. So in that case, dy dx is equal to 1 over x ln 2 plus 1 over x plus sine x plus 3e to the power 3x. So look at the next techniques quickly. The next techniques we are considering are the product rule and quotient rule. For the product rule, if y is equal to u times v, that's uv, where u and v are functions of x, it means that dy dx is equal to v du dx plus u dv dx. That means this function v will multiply the derivative of u with respect to x, and the function u will be multiplied with the derivative of v with respect to x. Then we take the sum of the two of them. Whereas for the quotient rule, if y is equal to u over v, that's quotient means division, then dy dx is equal to v du dx minus u dv dx over v squared. Take note, we don't have over v squared here. We just have plus, but here we have over v squared. So let's look at some examples to verify if these rules are correct. Let's say our u is equal to 4x squared and our v is equal to 3x squared. Now, it means that for product rule, y equal to u v is the same thing as 4x squared times 3x squared, and that gives us what? 4 times 3, 12x to the power 4. Then dy dx, 4 times 12, that gives us 48x to the power 3. So by using this rule, I want to see if we will get the same result. So here we have dy dx is equal to v du dx plus u dv dx. And what is our v? Our v is 3x squared into, what was our du dx? When you differentiate u with respect to x, you'll be having 8x. Then plus u, what was our u? 4x squared into, when you differentiate v with respect to x, you'll be having 6x. So here we are having dy dx is equal to 3x squared into 8x. That gives us 24x to the power 3. Then plus 6 times 4, that's 24. X squared times x, x cubed. So we still have 24x cubed. So 24 plus 24, we're having 48x cubed. So you can see that we got exactly the same answer. Now let's verify the quotient rule. Y is equal to u over v And this is the same thing as 4x squared over 3x squared. That's u over v. Then this gives us 4 over 3. So dy dx is equal to 0. Why is it 0? 4 over 3 is a constant. So when you differentiate a constant, you have 0. So let's verify using the rule we have. We'll be having dy dx equal to v du dx, and our v is 3x squared. Differentiate u with respect to x. You are having 8x minus u dv dx. Our u is 4x squared. Then into dv dx, differentiate v with respect to x. You have 2 times 3. That will give you 6x over v squared. What was our v? 3x squared. Then we square. This gives us 24x cubed minus 24x cubed over 3x squared to the power 2. 24x cubed minus 24x cubed will give you 0. So dy dx is equal to what? 0. So you can see that both methods gave us the same answer. So we can use the quotient rule to get the derivative of tan x. If y is equal to tan x, it means that y is equal to sin x over cos x. And this is equal to u over v. So dy dx is equal to v du, that's cos x, into differentiate sin x, you have what? Cos x. Then minus u dv, that's sin x. Then differentiate cos x, you have minus sin x, divided by v squared, that's cos x squared. So what do we have? Dy dx is equal to cos square x minus times minus plus sine square x over cos square x. But remember from trigonometry that sin square x plus cos square x is equal to 1. So we're having 1 over cos square x. Also from trigonometry, the inverse of cos x is called sec x. So since we're having 1 over cos square x, it means that the answer is sec square what? X. So dy dx is equal to sec square x. Let's look at the next techniques. The next technique we are considering is the logarithmic differentiation. It's called logarithmic because it has similarity with logarithm. Now here we have, if y is equal to uv, then 1 over y dy dx is equal to 1 over u du dx plus 1 over v dv dx. So you can see where we have y, we have 1 over y dy dx, u 1 over u du dx, v 1 over v dv dx. Now, but if y is equal to u over v, then 1 over y dy dx is equal to 1 over u du dx minus 1 over v dv dx. So v here takes a negative sign because it's a denominator. And that's what happens in logarithm, where plus indicates multiplication and minus indicates division. So if we combine the two expressions, we'll be having, if y is equal to uv over w, then 1 over y dy dx is equal to 1 over u du dx plus 1 over v dv dx minus 1 over w dw dx. So even if we have y equal to uvw over x z t, just use plus for the numerators and use minus for the denominators. That's all. Okay, let's verify if this rule is correct. For the first one, y is equal to uv, then 1 over y dy dx is equal to 1 over u du dx plus 1 over v dv dx. So what do I have? That dy dx is equal to y over u du dx plus y over v dv dx. But remember that your y is uv. So if I substitute for y in the equation, I'll be having the y dx is equal to uv over u du dx plus uv over v dv dx. Now v will cancel v, u will cancel u. So this gives us v du dx plus u dv dx. And you can remember that this is product rule. Let's verify the one for y equal to u over v. So we're having dy dx is equal to y over du dx minus y over v dv dx. Well, remember that your y is equal to u over v. So dy dx is equal to u over v will be giving us u over v u du dx minus u over v squared dv dx. So this will be giving us 1 over v du dx minus u over v squared dv dx. So if we multiply both sides of the equation by v squared, we'll be having v squared dy dx equal to, multiply here by v squared, have v du dx minus, multiply here by v squared, have u dv dx. So we divide both sides by v squared, as making dy dx the subject of the formula. We're having dy dx is equal to v squared will come over, and we'll be having v du dx minus u dv dx over v squared. So you can see that this is the same thing as the quotient rule. So we've been able to verify that this expression is correct. I want us to try one example. Now let's say we have y equal to u v over wt. Then our u is equal to ln x and v equal to 3x to the power 3. W equal to x squared, then t equal to 3x. So this implies that we're having ln x into 3x to the power 3, then divided by x squared into 3x. So 3x will divide 3x cubed, and we're left with x squared. X squared will divide x squared. So we're left with ln x. dy dx is equal to 1 over x. Now, we want to verify if we will get 1 over x using this logarithmic differentiation method. Now, since we have y equal to uv over wt, remember we got ln x as y before we differentiated. Now, let's see what happens if we use logarithmic differentiation method. We'll be having 1 over ln x dy dx equal to 1 over, that's for u, we are having ln x into du dx, that's 1 over x, plus for v, we are having 1 over 3x cubed. Then differentiate this, you'll be having 9x squared, then minus 1 over x squared. Differentiate this, you'll be having 2x minus 1 over 3x. Differentiate it, you'll be having 3. So what are we having? Here we are having 1 over ln x dy dx is equal to 1 over x ln x plus 3 divided 9, we'll be having 3. X cubed divided by x squared, we'll be having x. Then minus 2 over x minus 1 over x. Then this is the same thing as 1 over x ln x. Why is it the same thing as 1 over x ln x? 3 minus 2 minus 1, that gives us 0. Remember, we have 1 over x, 1 over x, 1 over x. Then we're having 3, 2, 1. So here we'll have 0. Then we are left with 1 over x ln x. That means dy dx is equal to, bring your ln x to this side of the equation. You'll be having ln x over x ln x, and that gives you 1 over x. So you can see that we got the same thing using this technique. Let's look at the next one, function of a function of x. So for this technique, function of a function of x, we have that if y is a function of x and u is also a function of x, then dy dx is equal to dy du times du dx. Now, take for instance, we have that y is equal to sine 2x. Now, let's say that 2x is u. So we have that y is equal to sin u. Let's get our dy du. dy du is equal to what? Cos u. Then let's get our du dx. Du dx is equal to 2. Why? Because u is equal to 2x. So when you differentiate to x, you have 2. Now, dy dx becomes 2 times cos u, which is equal to 2 cos 2x. So that's what differentiating the function of a function is. So here we call it function of a function because 2x is a function of x. Their sine is a function of a function of x. Now this applies to exponential functions also. We'll have y is equal to e to the power 3x. So what do? We say y is equal to e to the power u. Then dy du is equal to e to the power u. And du dx is equal to 3. Remember that this is our u. Then dy dx is equal to 3e to the power u, which is equal to 3e to the power 3x. So this is the same thing for the derivative of exponential functions. That's for e to the power kx. You'll be having ke to the power kx. Let's look at the next technique. The next technique we are considering is the differentiation of implicit functions. When the relationship between y and x is more involved, then a function of y is handled like a function of x with dy dx attached to it. What that means is this. If we have y, then we'll be having dy dx into 1. Remember, when you differentiate x, you have 1. Now, when we differentiate that y, we'll have 1 with dy dx attached. Then, when you differentiate y squared, you have 2y, then dy dx attached. When you differentiate sine y, you have cos y, dy dx attached to it. And when you differentiate e to the power y, you have e to the power y, dy dx attached to it. Just the same way you would have differentiated x. That's the same way you differentiate y. But you must attach dy dx to it. Then, we have an example, y squared plus 4x squared is equal to 5. So to differentiate, we apply what we just said. This gives us dy dx into 2y, then plus differentiate this, you have 8x, differentiate this, you have 0. So it means that dy dx is equal to minus 8x over 2y. And that's the same thing as minus 8x over 2 roots. Making y subject in this equation, we have 5 minus 4x squared. So that's what we have as our derivative for this function. So if you want to verify, you can make y the subject here and differentiate using any of the techniques we've already discussed. Let's look at the next technique. The next thing we are looking at is the differentiation of parametric equations. For example, we have y equal to sine t and x equal to cos t. So why are they called parametric equations? Because both x and y are functions of an independent variable t. So you can see that x is not an independent variable, it's a dependent variable. It's dependent on t. Likewise, y dependent on t. The same thing applies to this. Y is a function of t and x is a function of t. So since both are functions of t, how do we get our dy dx? We say dy dt dot dt dx is equal to dy dx. So for the first one, dy dt is equal to cos t and dx dt is equal to minus sine t. So dy dx is equal to dy dt, and dy dt is cos t, into dt dx. And dt dx is the inverse of dx dt, that's 1 over minus sine t. This gives us cos t over minus sine t, which is the same thing as minus cos t over sine t. Now we can verify if this is true using trigonometric identities. Here we have y is equal to sine t and x is equal to cos t. Remember that cos t is equal to root 1 minus sine squared t. That's from sin squared t plus cos squared t equal to 1. So in that case, we'll be having that x is equal to root 1 minus sine squared t. Then sine t is y. So what we'll be having is that x is equal to root 1 minus y squared, which means that x squared is equal to 1 minus y squared. And that means that y squared is equal to 1 minus x squared. So when we differentiate, we'll be having 2y dy dx equal to 0 minus 2x. Now we have 2 here, we have 2 here. So dy dx is equal to minus x over y. What's our x? Our x is cos t and our y is sine t. So we're having minus cos t over what? Sine t. You can see that both answers are the same. Let's try the next one. Here we have y is equal to 4t squared plus 5 and x is equal to 2t. So which means that y is equal to x squared plus 5. Then dy dx is equal to 2x plus 0, which is equal to 2x. But remember that x is equal to 2t, so we have what? 4t. Now let's see if we can get it using the other method. So we have that dy dt is equal to 8t plus 0. Then the x dt is equal to 2. Here we have 8t as our answer, and here we have 2. Now dy dx is equal to dy dt, that's 8t into dt dx. But here we're having dx dt, so we take the inverse, that's 1 over 2, and that gives us 8t over 2, which is equal to 4t. So you can see that both of them gave us the same answer. So that's how to handle parametric equations. You just do dy dt into dt dx or dy du into du dx, whatever you're using as your variable. So before we conclude this lesson, we'll be looking at applications of differentiation. I'll be talking about 2 applications, after which we solve 2 examples and we are done. The equation for the position of a wave is giving us y is equal to a sine wt. So I want to get the equation for the velocity of the wave. I remember when I was in secondary school, I struggled so much to understand this because then I only knew about general mathematics. I didn't do further maths in secondary school, so I didn't know how to go about this. When I saw it in some textbooks, I tried using algebra, using everything I knew as at then, to see if I could get the relationship between the equation for the position of the wave and the equation for the velocity and even the acceleration. But everything I did, I couldn't get it. But now looking back, I laugh because now I can see that it's not about algebra, it's about calculus. So please pay attention as we look at it. So what do? We simply differentiate. As to get your velocity, velocity is giving us dy dt. So we are differentiating this equation with respect to time, meaning that a here is a constant, w is a constant. A is the amplitude of the wave, whereas w is the angular velocity of the wave. Now, using product rule, we'll be having a times differentiate sine wt, you'll be having w cos wt. Then plus, you'll be having sin wt multiplying times differentiate a, you'll be having 0. So in that case, v is equal to aw cos wt. So this is the equation for the velocity of the wave. Now let's get the equation of acceleration from here. What do? We simply differentiate. Acceleration is given as dv dt, that's the rate at which velocity changes with time. So meaning that we have to differentiate this with respect to time. Remember, a and w are constant, they don't change. Our variable here is t. So in that case, we'll be having differentiate aw times differentiate cos wt, you have w into minus sine wt, then plus, we're having cos wt, differentiate aw, you have what? 0. That means we're having minus aw squared sine wt. Now, I want to see how y relates to v and relates to acceleration, that's alpha. So we have y over v is equal to a sin wt over aw cos wt. Now a will cancel a. Sin wt over cos wt is same thing as tan wt. Then we have w at the denominator. This implies that wy is equal to v tan wt. So you can see the relationship between y and v. If we make y subject, we have that y is equal to v tan wt over w. So between v and alpha, we'll be having alpha over v is equal to minus aw squared sin wt over aw cos wt. So we have minus, a will cancel a, then w squared divided by w, we have w, sin wt over cos wt, that is tan wt. So you can see that alpha is equal to minus wv tan what? Wt. Finally, let's look at the relationship between y and alpha. So we are having that alpha over y is equal to minus aw squared sine wt over a sine wt. Now we're having minus, a will cancel a, then w squared is here, sin wt will cancel sin wt, so in that case, we only left with minus w squared. So alpha is equal to minus w squared y. If you check your secondary school textbook, you will see this relationship, that the acceleration of the wave is equal to minus w squared y. Here y is the equation for the position of the wave, and w is angular velocity. Now let's look at the second application of differentiation, that's maximum and minimum points of a curve. Assuming you have a graph, a curve can be like this, also a curve can be like this, also a curve can be like this, so whichever one. But irrespective of the shape of the curve, we usually have maximum and minimum points. Now look at here, here is a minimum point, whereas here is a maximum point. So how do we get it using differentiation? We have that for maximum points, dy dx is equal to 0. The square y, the x square is less than 0. Whereas for minimum points, the square y, the x square is greater than 0. So for both of them, the y dx is equal to 0. But how do we know whether it's a minimum or a maximum? So the square y dx square is less than 0 for maximum, and the square y dx square is greater than 0 for minimum. So it's a kind of inverted relationship. For maximum, we're having less than. For minimum, we're having greater than. Now take for instance, you have this function 2x squared plus 5. Use your graph plotter you plot, you will notice that the curve is something like this, which means that it has a minimum. How do we verify using what we said? We differentiate. We'll be having 4x plus 0 is equal to 4x. That's dy dx. And we say dy dx is equal to 0. So dy dx is equal to 0 is equal to 4x. That means x is equal to 0. Now, this answer implies that the minimum or maximum point is at x equal to 0. That's at the origin. But we are not still sure if it is a minimum or maximum. In that case, we take the second derivative for this function. And the second derivative, that's the square y, the x square, is equal to, differentiate for x, you have 4. And you can see that 4 is not less than 0. Instead, 4 is greater than 0, which implies that this function is minimum at x is equal to 0. That means at that point where x is 0, the function is minimum. So these are the possible applications of differentiation. Let's solve 2 questions before we wrap up. These are the 2 examples I want us to look at. First one, we have y is equal to cos inverse of x. Find dy dx. And second one, y sin x is equal to x cos y. Find dy dx at pi, pi over 2. Now, for the first one, we are asked to get dy dx. What do? We make x the subject of the formula. So we are having x is equal to cos what? Y. What else do? We differentiate y with respect to x. So in that case, we'll be having 1 is equal to, when you differentiate cos y, you have minus sine y into dy dx. This implies that dy dx is equal to minus 1 over sine y. Also, differentiate x with respect to y. And that gives us the x dy is equal to minus sine y. Then dy dx, invert this, that's minus 1 over sine y. So any of the methods will give you the same answer. So we're having minus 1 over sine y. But remember that sine y is the square root of 1 minus cos square y. So in that case, dy dx is equal to minus 1 over root 1 minus cos square y. That's from sin square y plus cos square y equal to 1. That's where you get this from. And we're having minus 1 over square root of 1 minus cos y is x. So substituting for cos y, we're having what? X squared. So dy dx is equal to minus 1 over square root of 1 minus x squared. So when you are given y equal to cos inverse of x, this is the derivative. You can try for y equal to sine inverse of x. For the second one, we'll have y sine x is equal to x cos y. Now you can see it's very difficult to make y subject of the formula here, because here we are having y sine x and here we are having x cos y. Y is an angle here, but that's y is not an angle here. So what do? You just differentiate using what you are taught. Apply product rule here and apply product rule here. So we'll be having y into differentiate sine x. You have cos x, then plus sine x into differentiate y. You have dy dx. Then equal to, we have x, differentiate cos y, you have minus sine y dy dx. Then plus cos y, differentiate x, you have 1. So in that case, we are having y cos x plus dy dx sine x equal to minus x sine y dy dx plus cos y. So we can make dy dx the subject of the formula just by collecting like terms. This will cross over, and you'll have that dy dx is equal to y minus y cos x over, we'll be having some x, x. We have cos y minus y cos x over sin x plus x in y. where our y is equal to pi over 2, and that's the same thing as 90 degrees. If you use this formula, x over 2 pi times 360, you convert pi over 2 to degrees, it gives you 90 degrees. So cos 90 is equal to 0 minus y, that is still pi over 2. Here, y is not an angle, so in that case, we'll use pi over 2, which is the gradient. Then we're having cos x. X is 180 degree. Then cos 180 degree gives us minus 1 over sine 180, that gives us 0 plus x is pi. Then we're having sine y, that's sine 90, which is equal to 1. It implies that the y, the x, is equal to 1 over 2. So we've come to the end of this lesson. Thank you for watching. Please do well to like, comment, share, and subscribe. Once again, thank you for watching. God bless you.